June 4, 1942, 14,000 feet above the Pacific Ocean northeast of Midway Atoll, Lieutenant Scott McCuskey pushed his FO4F Wildcat's fuel mixture lever forward to full ridge and pulled back on the stick. The Pratt & Whitney R-1830 engine roared, its supercharger whining as McCuskey tried to gain altitude on the Japanese Zero, climbing effortlessly above him. The Zero's pilot rolled inverted, looked down at the struggling American fighter, and climbed away at 3,100 feet per minute. McCuskey's Wildcat, straining at maximum power, managed 2,265 feet per minute. The difference wasn't pilot skill or aircraft design. It was chemistry. The Zero's Sakai engine ran on 100-octane aviation fuel. McCuskey's engine burned 87-octane. That 13-point difference translated to 30% more power at combat altitude, and in aerial combat, power meant life or death. Before we continue with the video, if you're listening right now, help me prove something wrong. My wife said I wouldn't even reach 1,000 subscribers, but I believe stories about old machines like this deserve to be heard. Help me show her that these videos matter. Please subscribe to our channel, and let's keep these old machines' legacies alive. Below, 6 American aircraft carriers maneuvered against 4 Japanese carriers in what would become the turning point of the Pacific War. American pilots flew with courage that would enter legend, but they flew with fuel that gave away a decisive advantage before the first shot was fired. Japan's aviation fuel came from captured Dutch East Indies refineries, sophisticated facilities producing high-octane gasoline American pilots could only dream about. Germany's Luftwaffe operated on similar fuel, stockpiled before the war and synthesized from coal during it. The Axis powers had solved the octane problem. America had not. But 2,000 miles east in Baytown, Texas, a different reality was emerging at the Humble oil refinery. While McCuskey fought to keep his Wildcat, in the fight, chemical engineers monitored a massive steel tower where powdered catalyst flowed like liquid through pipes, carrying vaporized crude oil at 900 degrees Fahrenheit. The process had no dramatic name, just an industrial designation: fluid catalytic cracking. Inside that tower, hydrocarbon molecules were being rearranged, broken apart, and rebuilt into configurations that nature never produced. The output wasn't ordinary gasoline. It was 100-octane aviation fuel, and the Baytown unit was producing 13,000 barrels of it every single day. The irony was absolute. American refiners were perfecting a chemical process that would render Japan's fuel advantage obsolete within 18 months. But in June 1942, production couldn't scale fast enough. American pilots died fighting with inferior fuel, while American chemists invented superior fuel they couldn't yet deliver. The question wasn't whether American technology could match the enemy. The question was whether it could scale from thousands of barrels per day to millions before the war was lost. This is the documented story of how American petroleum engineers solved the octane problem, how a French mechanic's experiments became America's secret weapon, and how chemistry turned the tide of the air war more decisively than courage ever could. Octane rating measures one thing: a fuel's resistance to premature detonation inside an engine cylinder. When gasoline ignites too early, before the piston reaches the top of its compression stroke, the resulting knock destroys engines within hours. Higher octane fuel tolerates higher compression ratios, and higher compression ratios extract more power from the same volume of fuel. The problem was fundamental. Crude oil pumped from the ground produces gasoline that naturally measures 40 to 60 octane. Nature gave humanity low-octane fuel. Modern aircraft engines demanded high-octane fuel. The gap between what nature provided and what war required would define the air war's outcome. Thomas Migley, Jr., born May 18, 1889 in Beaver Falls, Pennsylvania, found the first solution while working as a mechanical engineer at General Motors in 1916. After testing thousands of compounds, Migley discovered that adding tetraethyl lead to gasoline boosted octane ratings dramatically. By 1925, nearly every American refinery added TEL to their gasoline, pushing octane from 55 to 70 or 75. Revolutionary, but limited. No amount of lead could push straight-run gasoline beyond 80 octane. The molecular structure simply wouldn't support it. Across the Atlantic, Eugene Houdry was arriving at a different answer. Born April 18, 1892 in Daumont, France, Houdry trained as a mechanical engineer but spent his weekends racing automobiles. Poor fuel performance frustrated him. Between 1922 and 1925, Houdry experimented with clay catalysts in his workshop, heating gasoline in the presence of specially prepared clays. The results astonished him. The catalysts didn't just break large molecules into smaller ones like conventional thermal cracking. They rearranged molecular structures, transforming straight-chain hydrocarbons into branched molecules that resisted knock. The output measured 90 to 95 octane without any additives. French Petroleum Company rejected Houdry's process between 1925 and 1927. American companies dismissed catalytic cracking as laboratory curiosity, impractical for industrial scale. Finally, in 1930, Vacuum Oil Company, which would later become Mobil, partnered with Houdry. 3 years later, Sun Oil Company invested $11 million in the first commercial Houdry catalytic cracking unit. On a spring morning in 1938, the unit at Paulsboro, New Jersey came online, producing 2,000 barrels per day of 100-octane aviation gasoline. It worked, but 2,000 barrels per day wouldn't win a war. By 1941, when Pearl Harbor burned, America operated exactly 7 Houdry catalytic cracking units. Total production: 14,000 barrels per day of high-octane fuel. Germany had stockpiled reserves sufficient for 2 years of intensive air combat. Japan controlled Dutch East Indies refineries, producing 100 octane in quantities that dwarfed American output. The catalytic process worked perfectly. It simply couldn't scale fast enough. Then, in laboratories at Standard Oil of New Jersey, Standard Oil of Indiana, and Texaco, 3 teams of engineers simultaneously invented something better. They imagined catalyst that flowed like water. Warren K. Lewis stood in his MIT laboratory in 1938, staring at a beaker of powdered catalyst. The Houdry process used solid beds of catalyst that clogged with carbon deposits after hours of operation. Refineries had to shut down, burn off the carbon, then restart. Lewis asked a simple question. What if the catalyst could move? What if it flowed continuously from reactor to regenerator and back again, never stopping, never clogging? He ground the catalyst into powder so fine it behaved like liquid, 140 mesh, particles smaller than flour. When air blew through the powder, it flowed upward through pipes like water. At Standard Oil of Indiana's Research Center in Whiting, Homer Martin was grinding catalyst to the same consistency, working toward the same insight. At Texaco, working with Universal Oil Products, engineers led by J.W. Bill Egan were developing moving bed designs with similar goals. 3 companies working independently, solving the same problem simultaneously. None knew the others were so close to breakthrough. The concept was elegant. Powdered catalyst enters a reactor vessel at 900 degrees Fahrenheit. Vaporized crude oil mixes with the flowing catalyst. Hydrocarbon molecules crack and rearrange on the catalyst surface. The catalyst, now coated with carbon deposits, flows into a regenerator where air burns off the carbon. The heat from burning carbon keeps the entire system hot. The clean catalyst flows back to the reactor. Continuous operation. No shutdowns. No waiting. On May 6, 1940, Standard Oil of New Jersey started the first commercial fluid catalytic cracking unit at their Baton Rouge refinery. Initial capacity measured 13,000 barrels per day. more than 6 times larger than any Hudry unit. The octane rating of the gasoline coming out ranged from 94 to 100 depending on conditions. For the first time, truly industrial-scale production of high-octane fuel became possible. War was already consuming Europe. The Battle of Britain raged from July through October 1940. Spitfires and Hurricanes desperately needed 100-octane fuel to match German aircraft performance. Winston Churchill sent urgent messages to Franklin Roosevelt. Britain needed high-octane fuel more than aircraft. British refineries couldn't produce sufficient quantities. American FCC plants became strategic assets 6 months before Pearl Harbor. In December 1940, 4 major oil companies made an unprecedented decision. Standard Oil of New Jersey, Standard Oil of Indiana, Texaco, and Anglo-Iranian Oil formed a patent pool. Competitors agreed to share fluid catalytic cracking technology for the duration of the emergency. Patent lawyers who spent careers protecting intellectual property now drafted agreements to give it away. The threat was existential. Commercial rivalry meant nothing if Germany won. Throughout 1941, 14 new FCC units began construction across America. Texas, Louisiana, California, Oklahoma, Pennsylvania. Total investment reached $134 million, equivalent to $2.8 billion in today's money. Construction started before America entered the war, driven by Lend-Lease priorities and the certain knowledge that war was coming. When Japanese bombs fell on Pearl Harbor December 7, 1941, America's FCC capacity stood at 180,000 barrels per day. Germany produced 400,000 barrels daily from synthetic fuel plants and captured refineries. Japan controlled Dutch East Indies facilities, making 150,000 barrels per day. American production lagged behind both enemies, but American capacity could grow exponentially. Enemy capacity could not. January 1942, 23 FCC units operated across America, producing 230,000 barrels per day of 100-octane aviation fuel, sufficient for roughly 30% of Allied aviation needs. In April, Lieutenant Colonel Jimmy Doolittle's B-25 bombers lifted and off the carrier Hornet's deck, loaded with fuel and bombs. The aircraft barely made it airborne, staggering into the sky with inches to spare. The 100-octane fuel gave them the power they needed. Barely. By January 1943, 42 FCC units were operational. Production reached 514,000 barrels per day. Refiners had developed an even better grade. They called it 100 over 130, 100 octane in lean, mixture, 130 octane in rich mixture. Republic P-47 Thunderbolts running on 100 over 130 fuel generated 2,800 horsepower. The same engines on 100 octane produced 2,000 horsepower. That was 40% more power from chemistry alone. No changes to the engine itself. Each FCC unit required more than 3,000 tons of steel, 18 to 24 months construction time, and specialized refractory materials that were scarce during wartime. Trained operators didn't exist. The technology was too new. Refineries recruited chemical engineers from universities, trained them for months, then put them in control of units processing 50,000 barrels per day of petroleum at temperatures that could melt steel if anything went wrong. They worked 3 shifts, 24 hours per day, 7 days per week for the entire war. At Humble Oil's Baytown refinery in Texas, 2 FCC units operated in 1942. By 1945, 6 units were running, producing 145,000 barrels per day. That was larger than Japan's entire aviation fuel production. Standard Oil's Baton Rouge facility expanded the original 1940 unit and added 4 more by 1944, becoming the world's largest high-octane producer. Shell's Martinez refinery in California supplied the Pacific Theater directly, reducing shipping time compared to Gulf Coast facilities. 3 FCC units came online there by 1943. The catalysts themselves became a crisis. Powdered silica alumina wore out. Early units needed complete catalyst replacement every 30 days. Catalyst production became a bottleneck threatening the entire program. Davison Chemical Company in Baltimore went into emergency expansion mode. In 1941, they produced 500 tons of catalyst per month. By 1944, production reached 12,000 tons per month, a 24-fold increase in 3 years. Distribution required innovation as dramatic as production. German U-boats hunted tankers in the Atlantic. The solution was pipelines. Between 1942 and 1944, construction crews laid 1,254 miles of pipeline from Texas to New Jersey. The Big Inch carried crude oil east. The Little Big Inch carried refined products back. Pipelines were immune to submarine attack and flowed continuously 24 hours per day. In the Pacific, pilots noticed the difference immediately. F4PF, Wildcats with 100-octane fuel, finally climbed as fast as Japanese Zeros. Not because the Wildcats improved, but because the fuel did. By 1944, F6F, Hellcats and F4U Corsairs, running 100 over 130 fuel, outperformed anything Japan could field. The fuel advantage that cost American lives in 1942 became the fuel advantage that guaranteed victory by 1945. Germany understood catalytic cracking existed. German chemists knew American refiners were producing high-octane fuel in enormous quantities. They simply couldn't replicate the process. The technical barriers were absolute. Manufacturing silica alumina catalyst required pure silica sources from specific clay deposits, precise pH control during production, and spray drying equipment, uncommon in the 1940s. Germany attempted catalyst production in 1943 and 1944. The results were inconsistent quality and rapid degradation. German metallurgy was the world's finest. Catalyst chemistry required different expertise they didn't possess. The reactor engineering presented equally insurmountable challenges. Fluid bed reactors operated at 900 to 1,000 degrees Fahrenheit under 10 to 25 pounds of pressure, while circulating 10 to 50 tons of powdered catalyst per minute. Preventing catalyst from escaping while maintaining continuous flow was an unsolved problem without American know-how. Temperature control required precision within 10 degrees or runaway reactions occurred. 1940s instrumentation was primitive. American refineries employed teams of engineers monitoring every parameter continuously. Germany had neither the i.e. knowledge nor the resources to match this effort. Germany's alternative was coal liquefaction. IG Farben operated 39 synthetic fuel plants by 1943, producing 175,000 barrels per day through the Fischer-Tropsch process. The chemistry worked reliably, converting abundant German coal into liquid fuel. But the octane rating topped out at 85 to 87, insufficient for modern aircraft engines. They added tetraethyl lead, but lead supplies were limited. Near Leipzig, the Leuna Works employed 35,000 workers, Germany's largest synthetic fuel facility. Between May and September 1944, Allied bombers dropped 6,552 tons of bombs on Luna alone. Production never recovered. Even undamaged, Luna couldn't produce 100-octane fuel. The chemistry simply wouldn't allow it. Ploiești in Romania provided Germany's only significant crude oil source. Production reached 175,000 barrels per day in 1943, but the refineries lacked FCC capability. Conventional refining with tetraethyl lead addition produced a maximum of 87 octane. On August 1, 1943, 177 B-24 Liberators attacked Ploiești in Operation Tidal Wave. 53 bombers were lost. Ploiești was damaged, but not destroyed. Destruction wasn't necessary. The refineries simply couldn't make high-octane fuel regardless of damage. Japan's situation was even more desperate. Before the war, Japan imported 80% of its oil from the United States. The July 1941 American oil embargo forced Japan's hand. The December invasion of the Dutch East Indies was specifically to capture oil refineries. The Palembang refineries in Sumatra and facilities in Java had pre-war capacity of 150,000 barrels per day. Japanese forces captured them largely intact in February 1942. But the refineries required Dutch technical expertise that evacuated spare parts that couldn't be replaced and catalyst supplies that couldn't be manufactured. Production never exceeded 45,000 barrels per day under Japanese operation. Octane ratings declined from 95 in 1942 to 87 by 1945 as catalyst supplies were exhausted. American submarines sank 8.9 million tons of Japanese shipping between 1942 and 1945. By war's end, Japan had more refining capacity than crude oil to refine. On August 15, 1945, Victory over Japan Day, 89 American FCC units were operational with combined capacity exceeding 1 million barrels per day of high-octane aviation fuel. More than the entire rest of the world combined? In the war's final 6 months, Japanese kamikaze aircraft operated on 70-octane fuel, while American carrier aircraft ran 100 over 130 throughout. The difference wasn't courage or tactics. It was chemistry scaled to industrial proportions no enemy could match. The Marshall Plan between 1948 and 1951 included refinery reconstruction across war-torn Europe. American companies licensed FCC technology to Shell, BP, and Total. The process that won the air war became the global standard for gasoline production. By 1950, refineries across Europe were adopting fluid catalytic cracking, transforming American wartime innovation into peacetime prosperity. The jet age required different fuel. Kerosene-based JP4 and JP5 replaced high-octane gasoline for military aviation. But FCC units adapted easily, modified to produce jet fuel with the same catalytic principles. During the Korean War from 1950 to 1953, American F-86 Sabres and Soviet MiG-15s both used kerosene-based fuel. American fuel quality remained superior. Fewer engine failures, better cold weather performance, higher reliability. Commercial aviation exploded in the 1950s and 1960s with Boeing 707s, Douglas DC-8s, and Convair 88s. Every jet airliner depended on fuel refined through processes descended from wartime FCC technology. The catalytic cracking process that powered B-29 superfortresses over Tokyo now powered passenger jets crossing the Pacific. But the impact extended beyond aviation. Higher octane automobile gasoline enabled higher compression engines with better fuel economy. The chemistry developed for war transformed civilian transportation. Today, approximately 400 FCC units operate worldwide with combined capacity exceeding 16 million barrels per day. The process remains dominant for gasoline production 84 years after the first unit started in Baton Rouge. Modern catalysts use zeolites instead of silica alumina, and yields have improved from 65% to 80%, but the core process remains unchanged. Catalytic molecular rearrangement at high temperature with continuous catalyst regeneration. The chemistry Eugene Houdry pioneered in a French workshop in the 1920s still powers global transportation. Eugene Houdry died July 18, 1962 in Upper Darby, Pennsylvania, holding more than 100 patents. He never profited enormously from catalytic cracking, having sold his patents early. He received a Presidential Certificate of Merit in 1948 for wartime contributions. Today, he's largely forgotten. Warren K. Lewis taught chemical engineering at MIT from 1910 to 1957 and died March 9, 1975 at age 94. FCC development was one contribution among many. He never sought recognition. Thomas Midgley Jr. died November 2, 1944, strangled by an elaborate pulley system he invented to help himself out of bed after contracting polio. His legacy is complex. Tetraethyl lead and chlorofluorocarbons both caused environmental damage he never anticipated. The statistics tell the story clearly. In 1941, American high-octane capacity was 180,000 barrels per day. By 1945, capacity reached 1,020,000 barrels per day, a 467% increase in 4 years. The P-51D Mustang, running 100/130 fuel, achieved 437 miles per hour, with 8-hour range using drop tanks. The German Bf 109K on paper could reach 452 miles per hour, but real-world Luftwaffe performance degraded constantly due to poor fuel quality. Range barely exceeded 3.5 hours.